Hi, I'm Professor Goins. In this video, I'm going to look at integrals of trig functions using what are called Pythagorean conjugates. Alright, so let me introduce the idea of a Pythagorean conjugate. Remember the Pythagorean identity. Sine squared plus cosine squared is 1. Well, I could rewrite this. Let's say I solve for cosine squared as put 1 minus sine squared on the left. So if I've got 1 minus sine squared, that's equal to cosine squared. This right here is the difference of squares, so I could factor that as 1 plus sine of x, and then 1 minus sine of x is equal to cosine squared. Okay, so the idea is that if I have an integral with this, say in a denominator, and I multiply top and bottom by this, in particular when I multiply the bottom by it, that's going to eliminate the sign. So this right here is called the Pythagorean conjugate of 1 plus sine of x, or conversely, 1 plus sine is the Pythagorean conjugate of 1 minus sine. There's lots of other Pythagorean conjugates, so let me show you in a textbook right here. I'll put this up on the screen so you can always pause it and write this information down or refer back to it. But at the bottom of this page here, those are some of the common Pythagorean conjugates. And if you multiply those together, what you end up getting is a perfect square of another trig function. Okay? So let's see how this works with computing an integral. All right, so let's say I have the integral. Let's use the Pythagorean conjugate that I would have had up above. So let's say I have the integral of 1 over 1 plus sine of x. So notice a u substitution won't work, and integration by parts won't work. There's not any other sort of standard methods that would allow you to integrate this. But if I introduce what's called a Pythagorean conjugate, and I multiply both top and bottom by that value, or by that expression, okay, so I'm going to multiply both top and bottom by 1 minus sine of x. Okay, so what happens is the numerator is 1 minus sine of x. And your denominator, I've got 1 plus sine of x multiplied by 1. I've got 1 plus sine of x multiplied by 1 minus sine of x. And we see up above here, I take 1 plus sine and I multiply by 1 minus sine. And if I FOIL that, simplify it, I'm going to get cosine squared. Because 1 plus sine multiplied by 1 minus sine would simplify to 1 minus sine squared, but then 1 minus sine squared from the Pythagorean theorem gives you, or Pythagorean identity gives you a cosine squared. And then what I can do is I could separate the fraction here. 1 over cosine squared minus sine over cosine squared. Okay, the reciprocal of cosine squared is the secant squared. And then for the second term there, sine over cosine squared, we can use a u substitution. This first term here, of course, that should be standard. Antiderivative of secant squared is tangent. So therefore, this is going to give me this is equal to tangent of x minus integral sine over cosine squared. And again, I mentioned a u substitution, so let's write out the details. U is cosine, therefore du is minus sine. And notice for the minus sine of x, I've got a minus that I can take inside the integral, and then I've got a sine and then a dx, so that will all get incorporated into du. Therefore, this becomes tangent plus the integral of 1 over u squared du. Okay, we can write 1 over u squared as u to the minus 2, and that will allow us to use the power rule. And remember, the power rule for taking antiderivatives works the opposite way as the power rule for derivatives. So this is the result of a differentiation, which means what I started with had an exponent of 1 more. When I take the antiderivative, then I'm going to increase the exponent by 1, making that u to the minus 1, and then I divide by that increased exponent. And then this would be plus c, since this is indefinite. And then finally, what I'll do is I'll simplify this so it's a u in the denominator. I'll change this negative down here to make this a negative here, and then I'll replace u with cosine. So a couple different things to maneuver, but standard technique. So this is 1 over cosine plus c. And we can write 1 over cosine as secant, so this would be the tangent minus the secant plus c. So this is your antiderivative of 1 over 1 plus sine. Again, we accomplish that by using a Pythagorean conjugate. Okay. Let's set up another integral where we're going to use another Pythagorean conjugate. Okay, so let's take a look at the following. Let's look at the integral of 1 over, let's do 1 over secant plus 1. In this case, the Pythagorean conjugate is secant minus 1. Again, that's going to come from one of the Pythagorean identities where I solve for, say, 1 minus secant squared, and then 1 plus secant, 1 plus secant, 1 minus secant, and of course that's going to be equal to tangent squared. So that's going to allow me to get this out of the denominator, the secant. Okay, so anyway, this is going to be 1 over secant x plus 1, so that's what I'm starting with. And I'm going to multiply top and bottom by secant x minus 1 Okay, so this is going to give me integral secant x minus 1 on top, and let's go through all the details. When I FOIL this together, that would give me secant squared. Then I get minus secant plus secant minus 1, and then dx. So you can see in this denominator, the minus secant and the plus secant are going to cancel, leaving secant squared minus 1. Okay, so let me clean up this side, and then we'll continue evaluating. Okay, so this simplifies to secant minus 1 over secant squared minus 1. And remember that secant squared minus 1, again, is one of our Pythagorean identities. That's equal to the tangent squared. Therefore, this gives me okay. And if I separate that, this would give me, let's see, secant over tan squared minus, and then I've got 1 over tan squared. Okay. Secant is the reciprocal. So now let's turn everything into sines and cosines. Secant is the reciprocal of the cosine. So this would give me integral. The secant will put a cosine in the denominator. Tan squared is sine over cosine, so the reciprocal of that would be cosine squared over sine squared. And then 1 over tan squared, again, is the cotangent, which is cosine squared over sine squared. And let's see, so in this first one, I can simplify and cancel a cosine, giving me cosine x over sine squared minus, and then for that second integral, it looks like we could just write that as, well, let's leave it as cotangent. Okay, so then let's talk about each one of these. Let's separate the integral, because we'll integrate these differently. So first one, cosine over sine squared, and then minus integral cotangent squared dx. Okay, so for the first integral, we'll use a u substitution. For the second integral, we will use, let's see, so for cotangent squared, we can rewrite that using a Pythagorean identity. So we will look at these two separately. Let's call that integral 1, and let's call this integral 2. So for integral 1, again, I'm going to use a u substitution. I'm going to say u is equal to sine of x. Therefore, du is cosine of x dx. And therefore, this integral becomes 1 over u squared, which is u to the minus 2 du. So that's minus u to the minus 1 plus a constant c, which is negative 1 over u, which is sine of x, plus c, and we can simplify that to negative cosecant x plus the constant c. So that's what I get for the first integral. Box that off so we don't lose it on the board here. This was the first integral. So now we're going to need to do the second one, and I need some more space here. Let's see, I'll try to leave the current example up there. Section this off. And now let's look at the second integral. Okay. In other words, let's look at the integral of cotangent squared. So what I'm going to do with the integral of cotangent squared is I'm going to replace it with Pythagorean identity. So what Pythagorean identity gives me a cotangent? Well, what we can do, if you forget which one it is start with the fundamental Pythagorean identity. So sine squared, oops, that's still not dry up there. Okay. So start with, and this is how you can determine any of the Pythagorean identities that you need, is start with sine squared plus cosine squared is 1. And then knowing that I need a cotangent squared, well, remember cotangent is cosine over sine. That means I'm going to divide this thing by sine squared. So divide both sides by sine squared. That would give me 1 plus cosine squared over sine squared is 1 over sine squared. So that's 1 plus cotangent squared is equal to the cosecant squared. Therefore, what I'm going to do is I'm going to replace cotangent squared with cosecant squared minus 1. Okay. Because, well, certainly 1 is easy to take the antiderivative of, and then cosecant squared is something that comes up not as often as secant squared, but it comes up often enough. So this gives me negative cotangent x minus x and then plus c. And let me label this, I'll call this c1, and this is constant c2. All right, therefore the value of the integral is going to be this integral here plus this integral here, giving me the integral that we started with was what, 1 over secant plus 1, or 1 plus secant, however I wrote that. Let's say it was secant x plus 1 would then be equal to negative cosecant minus cotangent minus x and then plus some constant c, where c would be a combination of c1 and c2. So that's how you compute integrals using a Pythagorean conjugate.